Good morning. Thank you for coming to this talk on parallel ready code. I'd like to thank the organizers of DevOps for this amazing conference that we're at, and also for asking me to, giving me the opportunity to talk to you. So my question today is your code parallel ready? So you can't possibly answer that unless you know what parallel ready means, and that's the main purpose of what I'm going to talk about today. That's my logo. It asked for a logo at this, for me to put on the starting slide, and I thought I invented that for the occasion. So let me start off by just talking for a moment about myself, because you're meant to do these bio things. I hate them, so you can tell that. I always say this is just another way of saying I don't have a real job. I'm slightly known in the Java world as a co-author of what I always say, without any doubt, and nobody's ever contradicted me, is the best book on Java generics. Right, you got it. And my current projects are, well, they were for a while the Lambda FAQ, which unfortunately got a bit neglected because I got involved in writing the nth book, where n is a large number, on lambdas. And this is, every time I give talks like this, I say it's going to be out real soon, but it really is going to be out real soon. It'll be out in time for Java 1. That's the intention. It's really a serious intention this time. This book has been written. I've been lucky enough to have some quite close collaboration with the Oracle design team for Java 8, and I feel like you can get a lot more out of any API, of course, when you understand the designer's intentions and what they were thinking. So that's something of what I've tried to get over in the book. I'm going to try and get a bit of that over in this talk today. It's not going to be a systematic introduction to the stream, to lambdas, or to the Streams API, or anything like that. It's probably going to work best for you. It would work for you if you know anything about them at all. It would work well for you if you know anything about reduction in functional programming. If you don't know anything about those things, I hope you'll still get something out of it. But I hope you'll get a lot out of it, obviously. Parallel ready is a term that is introduced. I introduced in the book. It's not actually my original. I didn't invent the term. It was Brian Getz who suggested it. The idea comes from quite a long way back, and particularly from a talk, fairly famous talk that Guy Steele gave. I don't know, possibly some time ago. Where he talked, the title of the talk was "How to Think About Parallel Programming Not." And the key quote that he put forward, his slogan for this talk was that the best way to write parallel applications is not to have to think about parallelism. And the idea that he put forward was that enabling your code for parallel execution is just another example of the kind of automated resource management, which has been a big tradition, a constant sort of theme of the progress of programming over a really long period. And the examples he gives are moving from machine code to assemblers, then having linking loaders, automated register allocation, heap management, virtual memory, and so on. So with each one of these developments, you get an increased level of abstraction for the programmer, and therefore more expressive power to the language that they're using. And this expressive power is really important, because actually increasing the level of abstraction and allowing programmers to think at a more abstract level actually lets them have new ideas. I always think of a quote in this particular connection. I always think of a quote from Tony Hoare, who invented quicksort, which was a very innovative sorting algorithm at the time. And he said he had the idea for quite a long time, but he couldn't actually express it until Algol had introduced the idea of recursion in programming. And it was only at that point that he knew what he wanted to do, but he couldn't express it. So I think that actually raising the level of abstraction is going to be really important in programming. But at the same time, you've got to recognize some constraints as well. Each one of these innovations brings you new constraints, and people always complain about it very bitterly. I mean, I'm old enough to remember, I started in the industry long enough ago, that people were still debating whether or not moving to a high-level language was a good idea. Hey, we really like writing in assembler. It gets us close to the metal. And, there is stuff that you've got to give up for each one of these things. So if you start using a linking loader, it takes a huge amount of grunt work off your hands, because it means that you can have separate compilation, and your code can be linked at runtime, well, at load time. But you have now to give up the feature that you got very fond of taking advantage of absolute addresses in memory. The same way with heap management. Once you have heap management, as we have in Java, you've got to not only give up absolute addresses, which you did a while back, but now you've got to give up relative addresses as well. You don't know where your objects are in memory. So you give stuff up. There's a trade-off for each advance that we make. So that's the idea. So here's the new automated resource management. I don't want to get too ambitious about this, because we should be careful to say that parallelization, as we're talking about it here, is quite limited. I mean, there's quite a lot of controversy at the moment as to whether the niche that the parallelization of Java 8 addresses is sufficiently large to really justify the changes. I think it does, not just because it is quite a large niche, but also because the improvements we're going to get in the code are pretty substantial anyway. The way we're going to code, if we are assuming that our code is agnostic about the mode of execution, whether parallel or sequential, we're going to have much better code anyway. So it's a change that's worth making. What is that change? What are we going to have to give up? Well, we're going to have to retool our mental tool sets. Some old habits won't work anymore. We've been, we just have a kind of reflex about minimizing operation counts, because we use, I'm still quoting from Guy Steele's talk. Operation counts are a good proxy for overall execution time. We're going to have to be prepared to waste operations. Same with space. We're used to minimizing space, and we're going to have to give that up, because if we share data between operations, that's going to be a real restriction on parallel execution. And again, this is something that parallel programs will look like. They're wasting space. I mean, generally speaking, we're going to have to accept that we're going to do more work. We're going to waste work, or we're going to do more work in parallel programs. The idea is that we'll get it back in reduced execution time. And we won't always. I mean, you will probably have heard all the many provisos that people are putting in front of you, saying, don't automatically go parallel. There's many, many ordinary cases where going parallel is not a good idea, because it's not actually going to gain you anything. But you should still write your code as though you can, because it'll be like, it's sort of like when you're programming in the collections API, you program to an interface. You don't know what the characteristics of your program will be later on, the performance characteristics. So you can choose a new implementation. Same way, the choice between parallel and sequential is a choice to be made on non-functional grounds. It's just like, will my performance be improved in this particular case? Later on a different processor, different data set, you'll have a different answer. So we're going to have to be prepared to give up these optimizations. And the big thing that we're going to have to give up is linear decomposition. We're used to processing one thing at a time to accumulate results. And if you're thinking about parallel programming, the moment you see that last line, you know, that's not going to work. That's really not going to work. We're going to have to give up accumulators, and we're going to have to use divide and conquer algorithms. And that means we're looking for, where we were looking for accumulation, we're going to now be looking for symmetric merge operations. So I think, I'm guessing probably people have seen this kind of thing already. So I'm assuming I'm not telling you anything very new. But just to make sure, the kind of standard example that is always used for these things is adding up numbers. So I'll not be different. So here's a very simple piece of code. The top two lines here are just setting up an array of 100 integers, I think, 100 integers. And the second argument to this setAll method, which is new, I think, in Java 8, is a lambda. So location 0 will get the value 0, location 1 will get the value 1, and so on. So it's just a convenient way of setting up the array that you see at the top there. And then we're just going to loop over it in a way that is kind of fairly normal for us. And the execution tree for this is going to look like what I've shown on the right there. I mean, obviously, we're just going to do successive sums. We're adding each time to the accumulator sum. And that's what we're used to doing, and that's what we're going to have to give up doing, because that's clearly not fit for parallel execution. Because clearly, if you had different threads executing there, they're going to interfere with one another. So we need to have some kind of divide and conquer and a merge thing, and you see that in the next in this slide, this has got a reduction. The first two lines are still the same, and now we're making a stream out of that interarray, and we're streaming it over the reduce method, and that takes two arguments. The reduce method takes two arguments, like in this case 0 and 1, and returns the sum of them. And what that means is that although of course it could be executed sequentially, it can also be executed in parallel. So this execution is independent of this one, and then they can be merged together, and then you can add this one. So that's a random pattern. Here's a more realistic pattern of how it would be done. And here we've got the same processor is doing a significant number of operations in the same thread. You can see, if you go backwards and forwards between these two, you see these are two different patterns. The grouping of the operations is different. And so I've written at the bottom, associativity matters, because associativity is the law on an operation which says it's okay to group the operations in different ways. And that's going to be necessary for everything that we do in this kind of way, for these divide and conquer algorithms. So that looks... So associativity is one of the constraints that we're going to have to observe as a trade-off for this new expressiveness. So that's all pretty straightforward, and functional programmers have been doing this for 1 million years. And why would we want to do anything else? I mean, I could stop the talk here. Well, or could I? Because actually, this pattern doesn't work very well for Java. I mean, Java in particular. Why not? Let's have a look at this. Let's take a slightly more realistic example than adding numbers together. I'm going to look at mutable reduction now. I've called this Oprah's Problem because I got this nice graphic, which I should surely be sued for, which shows Oprah's favorite 10 books over the last decade. And Oprah's Problem is, how is she going to find a book in this list of 10 books? And you may say, well, she's Oprah. Why doesn't she just pay someone to do it? So we could change it into Jeff Bezos' problem, because he really does have to find a book in his row of books, but we know how much he hates paying people, so he's going to want an algorithm. So here's the algorithm that we're going to have. We know how many pages there are in each book, and we know how thick each page is. Right? So if we knew what the starting position in terms of the number of pages was on the shelf, we would know where the book started. Please don't talk to me about the thickness of the covers, and I don't want to know about that. So what we're going to try and do is accumulate keep a running total of the pages. This is called a prefix sum problem, and it's had quite a lot of attention recently. It's not completely trivial, but it's quite easy. I don't want to spend a lot of time. I'm not going to go over this example in huge detail. I want you to get the idea of it. If you want to know more detail, hey, buy the book, of course. What Oprah needs is a map from each book to its displacement, what I call the displacement on the shelf. So New Earth is the first one, so it starts at 0, and the next one is the Poisonwood Bible, and so it starts at a displacement. It starts at a displacement equal to the page count of New Earth, and so on. Right. So actually, we're not going to produce a map for her. We're going to produce a sequential data structure. Again, I'm not going to go through the derivation of it, but we're going to end up with a sequential data structure like this. It doesn't matter which one it is either. And we're going to have some value objects. I think I call them partial results in this. And these are going to have, and what they're going to contain is a page count for each book and its displacement along the shelf. We're going to build that up. And using divide and conquer, we're going to come down from the top. The books are coming along the stream from right to left. And we're going to come down from the top and gradually build this thing up. So you can see that an intermediate stage in it is going to be this one, where what we've done here is we've taken each book, we've projected it into a value object here, because books have presumably got a lot more data to do with their authors and the publication date and all that stuff. And then we've wrapped it in a singleton data structure here, and now we're going to have to merge them together. So getting from the top to the middle is kind of straightforward. It's a mapping stage. And getting from here to here is going to be a reduction stage. So that kind of looks a bit familiar. How's the mapping done? Well, first of all, we're going to have to project the book out into one of these objects. And then, crucially, we're going to have to wrap it in the sequential data structure. I've used an array deck there for reasons that you might see. But actually, it would work. You could do it with an array list if it was simple. I don't want to make things more complicated. And so the mapping stage is going to have to do that for every element of this every element coming down the stream. So we'll set that on one side and look at the reduction stage. The reduction stage now, we're starting from all these singleton things, and we're wanting to get down to there. I've added an extra one on because it didn't make much sense with only 3, so now it's 4. And an intermediate stage in this is going to be, since we're going to use divide and conquer, an intermediate stage is going to be where we manage to merge 2 of them, but we haven't merged the whole lot yet. So this is just obviously for the sake of demonstration. How do we get from this stage, this middle stage, down to there? Well, the answer is, if we know that the displacement of these, each one of these partial results here is structurally similar to the final result. So this is a list of 2 books, and it's sure enough the displacement starts at 0 because that's this list, and then the displacement of this book is equal to the page count of this one. So in order to promote this down to here, then what we've got to do is, for the combiner here, we've got to add the 2 numbers at the end of the previous segment. That's to say, the displacement of the last book plus the page count of the last book, make that into a new thing. And then we've got to add it to each one of these displacements in the next segment. Right? So this is divide and conquer applied to Oprah's problem. It's not rocket science. But what is actually quite interesting is that it's very hard to think of a good example of applying reduction to mutable objects. We have a problem because normally reduction doesn't work very well for mutable objects, and that's what I'm going to go on to explain. So this example actually took some work to produce. What's actually wrong with it? Well, there's actually quite a lot wrong with it. The biggest thing that's wrong with it is there's nothing wrong with it. There's nothing wrong with the reduction for immutable values. Functional programmers have been doing absolutely fine with it for a really long time. But now we're doing functional programming in a language which depends really heavily on mutable data structures, and particularly on containers. This stuff is going to be used for processing collections a lot. And the collections library is very heavily tuned towards mutability. I mean, you want to add an object to an array list, you don't expect to put that object into a singleton array list of its own, and then use add all to combine them. That's going to be really inefficient, but that's actually what we're going to be forced to here. We would like to use, there are other overloads of reduce, and you'll actually find in the Streams API, you'll actually find overloads of reduce, not only for primitives, but also for reference streams, which actually do have base values in them. But they're mostly not very much use at all. Why can't we use reduction over a base? I thought I'd ask this question. Reduction over a base, which is a kind of obvious thing to do here, rather than keeping on rather than the form of reduction. I'm using a form of reduction here, which always demands I've gone too far back, sorry. Which always demands 2 objects. Does that help? No, I'm just going to go through it. The combination here is always going to demand two objects, and they've got to be the same type. That's our problem. Our problem here is we've got to start off with things that are the container type, because the form of reduction that I've used here always uses has operands of the same value type. Now, of course, there are other reduction overloads. There's a reduction over a base, which actually allows you to add a single thing to it, but we can't use it for parallel programming. Do you know why not? I'll now get back to the slide where I departed from. I really need to learn the sequence of... right, good, okay. So why can't we use reduction over a base for parallel processing? Anybody know? I fell into this trap. I actually wrote an extended example that did exactly this. And they said, no, you can't do that. And then I looked at it and I thought, it's really not working. Okay, so the problem is that the assumption with reduction is that the identity that is the base that is used for reduction overloads is reusable. Right? So if you say I'm going to reduce over a base, that, say for example, I'm going to reduce summation over the base of 0, start with 0 and then add things to it. If you do that on a parallel stream, that value will be used by different threads. Now, of course, for mutable objects like containers, if the first thread has changed the value in it, then the second thread, deciding to use it as an identity, it's going to get the mutated value. It's no good. It won't work. So actually, reduction doesn't work, or it's really not very much use for mutable objects, and therefore very little use for reference streams generally. It's fine for primitive streams, but not very much use for reference streams. So we need to do this thing that I showed you with a single element container for every value, and that's really painful because what's going to happen is you've got a 1,000,000 element array, and you're going to have to make 1,000,000 new array lists or whatever they are. I've got them along the top, and wrap each one of these value objects, and then you're going to be using the add all method, which is how you combine two array lists. You can't use the add method because they've got to have the same type. You're going to be using the add all method to combine two arrays. And this might be really, really long. If it's a sequential algorithm, remember we're meant to be agnostic about how we're executing. If it's a sequential algorithm, that's what you're going to be using add all over and over and over again for 1,000,000 elements. I mean, that's just really not a very good idea. So this is the real pattern. Lots and lots of singleton additions. And then a combine. I mean, think of it. You've got 1,000,000 elements, and you've got, I don't know, 4 cores or 8 cores or 64 cores or whatever it is. There's relatively few combines for the number of additions you've got. Everyone with me? Do you get where I'm going with this? Any questions? Okay, so all right, now I'm sort of saying, well, that's going to be done in one thread, and this is going to be done in another thread, and we need to make those threads reasonably efficient. We'd like to give them an addition operation. Basically, what we need to do is have a form of combining elements using divide and conquer, which allows mutation as well, and therefore addition, as well as being able to combine things. So here's the alternative. So the alternative is the collection API, the collectors API. The alternative is collection. Collection is against reduction. So to create a collector, you've got to provide 3 functions. And one function is the supplier. That's the new empty container. Another function is the accumulator that allows you to add a single element to the container. And the third function is the combiner for combining 2 containers. And, actually, I lied to you. There's 4 functions. Well, so I put that in because I want to be complete. But we won't talk about finishers today because we don't really have time. The one thing I would say about finishers is that we actually, there's this big idea that functional programming or functional style programming doesn't allow mutation. But that's not necessarily true. What is more fair to say is it doesn't expose mutation. So actually behind the scenes, of course, the way that these collectors work is they do mutate things, but they don't expose it. They do it in a safe way, and they keep it away from possible thread interference in the rest of your program. And so sometimes the finisher is what's needed to take that you may have a lot of mutation going on behind the scenes, and then finally for the finisher, it spits out an immutable object. I think the best example of that is the way that strings are joined. They're actually joined using a string buffer. The collector for joining strings uses a string buffer internally, but then at the last minute it calls toString to spit out an immutable object. So the fact that it's using it internally doesn't matter. So here's what collection looks like with on the same diagram as before. The supplier creates a new empty container. The accumulator can be used lots of times, and in the case, for example, of adding to a list, the example I gave was. I said we weren't able to use the add method previously, but we can use it now because the accumulator doesn't assume, this pattern doesn't assume immutability. And then the combiner is add all, as before. And the advantage of this is, there are many advantages. You create many fewer objects. It's a very flexible pattern, and already there are lots of predefined collectors in the collector API. They're produced by factory methods, and the implementation of those can change over time as the library writers get to be more expert, and they learn better optimizations, and they learn and quite possibly they'll use new collections for them. So the collectors API is quite agnostic about the implementations, and already they do really useful things like, for example, managing concurrent access to non-thread safe collections. So you can do parallel accumulation to an array list, even though an array list isn't thread safe, and they will manage the thread interference for you. So there's a big plus here. It's a really good pattern, and I think it's original to Java 8. I mean, I know it is. So they're actually pretty pleased about it, and it's kind of not had enough attention on its own because everybody's sort of saying, oh, streams, streams, lambdas, and so on. But the collectors API is a real innovation, and it's worth saying. Oh yeah, highly composable. I'll try to show you that if I get time today. They're highly composable, and that's really a plus as well. So you can actually they're designed to be able to link them together. Collection is actually more general than reduction, it turns out. You can express any reduction as a collection, but although you can do the reverse, you can't do the reverse in a way that encourages concurrency. So let's have a look actually at the collectors API. I know this is quite a long thread I'm drawing out in this talk, but I hope you're kind of keeping with me from the original motivation through to where we're going here. So this is going to get a bit more detailed. I started out waving my arms, and now it's going to get a bit more detailed. There's two kinds of collectors here. One of I should say, first of all, the stuff I've been telling you there might have given you the idea that you had to write your own collectors, but that isn't the case. For most people, most of the time, you don't have to. The factory methods provided in the collectors utility class gives you a really large number of predefined collectors where they built in the way that I just described, and most of the time, you won't need to do anything else. The biggest problem with the collectors class and its factory methods is that there are so many of them that it's actually a bit difficult to distinguish them. So I always like classifications. And here's my classification. There are these standalone collectors which you can understand in their own terms. So these are, they start off with really simple ones, like things that will just take the elements coming down a stream and just put them into a list or into a set or into a map. That one's a little bit more complicated. And joining is the one that I referred to earlier, which takes strings and joins them together. These ones are the framework provides the supplier. So if you use the factory method to list, you'll get a collector which collects to an array list. That's the current implementation. But they might change that next week. Similarly, a hash set and so forth. If you want to supply your own supplier, provide your own supplier, then you can use one of these. To collection will cover to list and to set, and to map allows you to supply your own map. So these are relatively simple ones. Something a little bit more complicated are these ones here, the grouping by collectors, which do classification. I'm going to talk a lot about those in the next 21 minutes. And the great thing about, since I said the great thing about collectors was that they're composable, the way that you compose them is by using a standalone collector as the first, if you like, as the first function to be evaluated, and then you pass the results on to a downstream component. And there's a whole lot of downstream components, which I probably won't get much time to talk about. Most of these are duals of reduction methods. So the reduction, which I said didn't work very well, works better in this context. Collectors have been created to mimic the actions of these. So, for example, there's a count method, which is a reduction over streams. And what you might choose to do is use a collector like a classification collector, and then decide to count the elements at the end of it, and you would pass them on to a counting collector, and so on for the others. Mapping, I'll show you in a minute. So here's my example domain for the. I know it's a bit complicated, but stick with me. So here's an example of a simple collector according to my diagrams. The values come in from the left along the stream. Now, the streams go left to right in these diagrams. And what comes out at the right-hand side is, in this case, a stream of persons coming in, because the simple collector I'm using here is to set. Right? So I'm assuming I've got a collection of person, which is called people. And I'm streaming that along here, and then I want to collect it. The collect method of the reference stream is the one, or stream, sorry. The collect method is the one that you need here. And then in here, you put the collector that you actually want to use. So this one's been created by the factory method to set on collectors, and you will see how it works. Here comes an element. This collector supplies the supplier of the toSet collector is, of course, a new hash set, a hash set constructor, and it puts the element in there and does the same for any further ones that arrive. And in due course, when the stream is exhausted, as is about to happen, then at that point it spits out the finished product, which is a set of person. So you're thinking that's a very elaborate diagram for a not very complicated example, but you'll see. These diagrams are not there, are there for a purpose. So actually, I'm now skipping over all the simple collectors. I mean, if I wanted to show you how the to-map collector works, that would be a little bit more complicated. But fundamentally, these simple collectors, which will just collect to collections, right, as in the Java util collection sense, those are relatively straightforward. Now we come on to the classifying collectors. This is the other kind of simple collectors. And these are a little bit harder to understand. They take a function, and what they do is they use the classifier function to make a classification mapping, and so they put the result of the collection is in a map. Same classified objects are put by default into a list, but we'll see that you don't need to do that. So, for example, if I wanted to classify persons according to the city that they live in, I would get from that a map from city to a list of persons. So Amy and Bill live in London, and so London would map to a list containing Amy and Bill. Here's what the code would look like for that. The map is I've called people by city, and I'm streaming the person list here and collecting it into grouping by collectors created by this factory method. And the classification function is person get city. I'm using the method references in Java 8. You can think of it as a lambda if you want to. It's a function which takes each person to the city they live in. So here's the diagram for that. It's a little bit more complicated. So here we've got, this is a classification mapping here. Bill and John live in London, and Amy lives in Athens. And so here comes Bill, and he lives down the stream, and he lives in London. He goes into that list. And Amy lives in Athens, so she goes in that one. John lives in London as well, so he goes in that. Now, they're being put, by default, they're put into a list, one list for each element of the classification mapping, for each range object in the classification mapping. And finally, what it spits out when the stream is exhausted is the map from city to list of person. You don't necessarily want to put them into a list. So as I said, one of the big deals about collectors was that they're composable. So you'd kind of expect it would be really very rigid if that was your only option. So you can pass the elements as they've been classified down onto a downstream collector. So the classifier function makes a classification mapping, and the grammar of that isn't exactly right, and it places them. It's meant to parallel the earlier slide, which says they'll go into a list. Here it says they're going to go into a container defined by the downstream collector. So here, for example, I've decided, just a very simple example, I've just decided to replace the default list with a set. Right, to do that is really not very difficult. It's an overload on the grouping by. Here, as well as the classification function, you supply the downstream collector as well. Assuming a static import here, this is collectors.toSet. So that produces a collector, and this collector puts them into a set. The default was actually collectors.toList. But you can put any collector you want there. This is the diagram here. You've got to imagine now what we've got in here is not, I mean, I've kept it fairly simple because these animations are hell to make. They're really difficult. So you reuse them as far as possible. This collector here, which puts them into a set, isn't the only thing that you could have there. You could have lots of things. So in this case, Bill and John are now being collected into a set rather than being collected into a list as before. Right. Okay. I have to go through this. It's awful. And finally, we're going to get out our map from. City to set of people rather than list of people as before. But as I say, you could use any collector for that. Okay, so those are the simple collectors. What about the ones that are used specifically for composition? So I've used this for composition here, but it's also a standalone collector. Now there's some other ones which are really only suitable. You'd only ever use them as downstream collectors for composition. There's two of them. One of them is these ones that I mentioned earlier, the duals of reduction methods. I think you probably get the idea of those. Well, let me just say, if there was anything you thought you could do by reduction, like counting things or getting the maximum and minimum or I haven't got maximum, minimum there. You can get sums and averages. There's summarizing statistics as reduction methods. There's actually, and also there are the full long-form reduce methods, not these convenience ones, but actually the real deal. All of those are available in the Stream API, and there are duals for them as collectors to be used as downstream collectors in the collector API as well. There's also an extra one as well, the one I skipped over there, mapping. So the idea of mapping is that it'll project out a particular, well, not only project out, but it will actually apply a map to any element of a stream before it gets into a collector. So you might think, what's the use of that? Because I could just apply a map on the stream, on the incoming stream. Why do I have to have a collector to do that? Well, the answer is the reason why you want to have a collector to do that is you might want it to be sandwiched. You might want the mapping to be sandwiched between two different collectors, like in this case. In this case, what we're doing is we're getting the stream person. We're going to collect them. First of all, we're going to group them by age. So now we're getting parallel streams of persons classified by age. And then for each person, we're going to get the city that they live in. And that's what the mapping does. And then it passes it to another downstream collector, in this case to set. So we're going to end up with a series, if we've got people aged 15, 23, and 37, we're going to get a set of a set of the cities of the people aged 15, a set of the people aged 23, and a set of the people aged 37. So the picture for this isn't actually a very clever picture because it's only the right-hand side. Really, to get the point of this picture, you'd have to imagine a collector upstream from here. So what we're getting in here would be the 15-year-old, the stream of persons who've already been classified as 15-year-olds. There's not a lot of point to doing it as it is in the diagram, because what there is in the diagram you could reproduce just as easily by applying a mapping function to the stream before it got to the collector. But if you want to put a mapping in between two collectors, this is the way to do it. So you can imagine this is really going to be fairly similar to what we've already seen. Here comes a Bill. Let's say Bill's 23. All of these people are going to have to be 23 years old for this to work. Then you've got to imagine the same thing for each one of the other ages. And here the mapping is applied before the values are passed through to the subsequent collector. So it's like an adapter from one stream to another stream. What we have here coming in are streams of person, and what we have going out are streams of cities. And then they're being collected into a set according to that. Okay. Right. Oh, we have to work our way through this example. All right. Okay. So, that's it. 10 minutes to go. We now have questions and answers. The difference is, I'm going to ask the questions, you're going to give the answers, right? So my question is, right, our first problem is, I've only got 3 problems, so don't worry. I won't be picking people out from the audience, but I'm afraid I don't have any prizes. I should have thought of that. Sorry. People by age. Okay, this is meant to be quite an easy one. You want to look at the type that we're trying to produce. So we want to map from integer to list of person. What are we going to... And I've restricted these examples. I mean, the original talk had loads of different kinds of examples, which included lots of stream operations, intermediate operations on streams, like map and filter and so forth. But these are just going to use collection. Well, collectors, rather. So what's the collector that I need in order to be able to classify people? Grouping by, sorry? Age. Okay, grouping by, the age is in this case, this is the function itself that's going to project from it's going to take a person and going to give back the corresponding age. So that's going to give us that. Okay, right, so that was too easy. Okay, population by age then. Right, so what I want to know now is I want to know for each age how many people there are in that age. So, grouping by age. Right. Okay, so we know there's a stream reduce convenience method called counting, called count, and we know therefore there must be a collector that corresponds to it. And so there is. It's called counting. Excuse me. It's just brilliant. Eh? How does that always work? So since we knew there was a stream method called count, then we know there's going to be a collector called counting. That's a pretty good guess. Okay, I needed more than 3 problems. 8 minutes left. Sorry?
Quick question. How do we decide which one to use? The mapper, the reduce, or the collector reduce? What does the generic decide which one?
Okay, that's a really good question. Sorry, the question was, how do we decide which one to use? And what I'd really like to do would be to provide a kind of flow chart of, this is my problem, and this is how to find my way through it, because there's so many of these collectors' methods. And although the Streams API isn't very big, it's kind of quite dense. And actually finding your way through it's a real problem. And I'm still trying to think about that. I can't honestly say. I mean, in this case, my first thought, I'll just try and make this up as I go along. Well, I can see that I want to map from integer to long. Now, I know that obviously I know the semantics of this. I want it to be from age to the number of those people. So I know that I'm going to need to when I break this problem down, I see I'm going to need some kind of intermediate data structure which is going to have all the people of the same age in there. That's going to be the thing in the middle. I'm starting off with people of all kinds of ages. In the middle is going to be, I'm going to have separated them out into the different ages and clumped them together. And then the last stage is going to be to get a count of those. Now, that separating out, the thing about the separating out is that does suggest grouping by. All these problems, to be honest, all of these problems, all the interesting problems, and all the interesting things you can do with collectors, all start with the word map here. Right? So most of the time, for anything interesting you're going to do, you're often looking at grouping by. So it's kind of a bit of a cheat, that. I don't have a good answer to this, but I would suggest that you play with it for a while. I know a good book on the subject coming out shortly, and experience will tend to bring it to you. Okay, so here's the third one. I want names by age. Oh, I put names in there, didn't I? So we're going from age to a list of Did I have names? I didn't have names. Never mind. It doesn't matter. We assume we've got a get name. Assume we've got a get name method on there. How am I? Okay. So I've got grouping by to start off with. That's going to be okay. So I'm grouping by person got get age. So that's given us the split.
Map and person get name.
Too easy. Everyone with it so far? Well, this is a sandwich thing. What we've done is we've separated them out by age, but now we know that we want to. What are we going to do? We want to get their names in the end. We're going to collect those names into a list. So how do we get at the moment? What we get from this is a stream of person. So we need to map that into a stream of. We want to map that into a stream of name. Right. I'm just repeating what you've already told me. ToList is not by default ToList is by default for grouping by, but it's not by default for the mapping collector. And the reason it isn't, people quite often ask that question. The reason it isn't is because mapping is only intended to be used in this downstream context. It doesn't really make any sense to use it otherwise. And at that point, you probably don't. There's probably no sensible default to be chosen for what you would use. So you're going to have to say it. Yeah, mapping doesn't have an overload without the collector there. Okay, so that's the end of my examples, and the end of my half of the Q&A. To summarize, I haven't got a summary slide, so I just say the message is that we want our code to be agnostic as to to not care about the mode of execution. They've gone to a lot of trouble to make it really quite difficult to write code that will only execute sequentially. I mean, you can still do it. I mean, there's all kinds of tricks that you can do that will enable you to do that. But it's a bad idea because not only do you want your code to be possible, you want it to be possible to execute your code in parallel, but you believe it'll be better code if you do that. And that's actually going to be, I mean, that's actually the future of collection processing in Java. And I think, we should get with the future now. I think it's really quite exciting. I think they've done a very good job of bringing a lot of features from functional languages into Java without actually spoiling. I mean, given a kind of huge resistance to that in the history of Java, and also the history of Java programmers as well. They've done a pretty good job bringing it in and adapting the ideas of functional programming. And in the collectors API, there's actually a key innovation there which really makes functional programming work with a language that depends on mutability in a way that you would not have expected was going to be possible. So I think it's pretty exciting, and I think we should get with it. Thank you very much. We do have 2 minutes left if anybody does have any questions, but don't feel you have to stay, obviously. Yeah? Sorry, how do I solve? Oprah's problem. Oprah's problem. How do I solve Oprah's problem? Well, I solve it. The way I solve it, actually, the book has got 2 solutions in there, and they are coding of the algorithm I showed you there. It's a prefix sum algorithm, and basically what you do is you just, for each segment of the data structure, you take the displacement of the last element of the previous segment and its length, and you add that to every element subsequently. And you can do that with collections, you can do that with a collector, and you can do it with reduction. Actually, I do it with both of them. And I claim that, and I think it's pretty obvious, that the collector's version, which is quite similar, just a lot better. Okay. Thank you.